Ever wondered if math breakthroughs could be mass-produced? Well, August 1st, 2026, OpenAI's Astra model dropped 10 papers generated proofs across fields. But here's the kicker. They explicitly called out verification debt. That's the theme we're diving into today with DMath PROOFGENESIS 9. So what's the big idea behind this? It's not just about finding answers faster. It's about rethinking what a proof even is. Forget the old single endpoint view. We've broken it down into 7 distinct relations: genesis, necessity, world contact, mutual understanding, non-collapse, formal projection, and crucially, statement fidelity. Think of it like building with Legos. Each piece has its job. The real game changer? Recognizing that traditional math and semantic narrative aren't rivals, but partners with different jobs. This lets us look at those 9 famous unsolved problems: Goldbach, Riemann, Navier-Stokes, the whole gang, and see they share just 4 core structural challenges. It's like realizing all those different locks actually fit the same 4 types of keyholes. This isn't replacing math, it's giving us a new blueprint. Remember the Astra event, August 1st, 2026? OpenAI dropped 10 math results, supposedly cooked up by their Astra model. Humans polished the manuscripts, and the model even spat out lean certificates. Sounds like magic, right? Proofs generated in batches across different domains. The cost? Roughly $2,000 worth of reasoning tokens. But here's where it gets interesting. They didn't claim these solved everything. They specifically mentioned verification debt. Things like making sure the formal proof actually matches the original problem statement, ensuring no prior work was missed, checking resource costs, and so on. You can't just wave a magic wand and say verified, because the model is smarter now. That debt is real, and it's what keeps us honest. So, batch generation is a tool, but trust? That still needs rigorous checking. Okay, let's talk specifics. We're tackling the heavy hitters: Goldbach, twin primes, Collatz, Riemann, Hodge, BSD, Navier-Stokes, Yang-Mills. 9 massive problems. But thanks to our semantic lens, we see they boil down to 4 fundamental structural hurdles. First, mask non-saturation. Can local patterns really block all possibilities globally? Second, continuation or termination. Will sequences always end nicely, or could they loop forever? Third, duality or spectral separation. Is symmetry enough, or do we need something stronger? And fourth, local-global carriers. Can small-scale behavior predict the whole picture? This approach hasn't solved the original problems, mind you. Their status remains open. What we have are 12 new, machine-checkable theorems, barriers, or conditional bridges. Think of them as signposts pointing towards the solution, not the destination itself. So what did we actually close? 12 new theorems, barrier results, or conditional bridges. Things like the finite local mask non-saturation theorem, the unique witness black box lower bound, the insufficiency of Riemann symmetry theorem. These are solid machine-checkable steps forward. But the original 9 problems? Still wide open. The system keeps their status as original tracked open. The real breakthrough isn't just generating more proofs, it's identifying the precise remaining gaps, the decisive bridges that need crossing. Next steps involve dynamic masks, global potentials, separating observables. The big takeaway: verification debt isn't a hurdle to overcome, it's the very engine driving clearer thinking and targeted progress in mathematics. That's the future.